Okay, now we start the discussion for project some features of Miquel structures, and our speaker is Pavel Kozhevnikov. So Pavel, please.
Yeah, thank you, Nastya. And of course, it's impossible to discuss all the problems, so we'll concentrate our attention on some special things. In my opinion, on some nice details of this project. So first, about problem 11. Yes, if we reformulate this problem possibly in the most easy way, we obtain the following problem. Given, hopefully you see my screen. Yeah, given a triangle ABC, then arbitrary point M, and then on Sevians A, M, B, M, and CM, we take 3 points like M, A, M, B, and C, such that these 4 points M, M, A, M, B, M, C are concyclic. So we have this red circle. Then we construct more points like A prime, B prime, C prime on this circle. We construct them in such a way that line MA is parallel to BC and so on. And similarly, we construct the other points. And so in this construction, we need to prove that 3 circles are coaxial circles. 3 circles like A prime, MA, and 3 analogous circles are coaxial. So the solution, possibly the most easy solution, could be obtained by additional construction of additional points. So we can proceed on this figure and prolong the sides A prime, B prime, B prime, C prime, A prime, C prime, and obtain these new points of intersection with the side lines of the initial triangle, like A, B, B, A, AC, and so on. So using this red circle and equalities of inscribed angle and just angle chasing, we can easily obtain that these new points like A, B, and AC also lie on the circle A, MA, and MA prime. So this we have this green circle passing through points AB and AC. So by the way, of course, I skip some details. We'll present the solutions, or at least the sketches of the solutions for all the problem in the written form. So I skip some details like angle chasing and so on. So we have this green circle and 2 analogous green circles, and now we use these additional points A, B, B, A, and so on to apply the criteria for coaxial circles. So we now in this construction we have a chance to calculate in an easy way the power of a point, say, power of point A with respect to the other two green circles, like, for example, ABA times AAB, sorry, ABA times AB will be the power of point A with respect to the circle B and B prime. Yes, and then rewrite these powers of point in terms of ratios of length or signs, and relatively easy obtain that the ratio of these powers of points of a point A, of point say AB, and similarly the point AC with respect to the other two green circles. This ratio of powers is a constant. So by this known criteria, seems it's problem 6 of our project, we obtain the required statement. So by the way, this problem 11 is a relatively hard, difficult problem, difficult one of the most difficult in all the project. Though you see, everything could be done elementary, but a bit tricky using some extra points of intersection. Now let us move to the next problem. Problem 13. So we start from this general construction, arbitrary triangle ABC, and 3 pairs of points like A1, A2 on its sidelines. And then we construct this number of points like LA and so on. In fact, we do not need points LA, LB. We need only N, A, and B, and C in this construction. But by Miquel theorem, the most convenient way to obtain a point NA is to intersect the circles A, B1, C1, and analogous circle A, B2, C2. So this another definition of an A point, and it's more convenient to use it further. Yes, and these circles that we just drawn, they pass through P and Q respectively, of course. Next, sorry. We draw similar circles to obtain, say, NC. And I will try to solve this problem, to establish all the statements in this problem in another way, using these circles only, and possibly angle chasing. So basically this construction uses only circles and line, and it's natural to expect that possibly it could be solved by elementary methods only. Now let us try to prove first that on this picture the sorry, the circle, there is the circle passing through NA, P, Q, and NC, this circle. Now, by angle chasing and inscribed angles, try to calculate this angle NAP B1 plus B1 P and C. Yes, using inscribed quadrilaterals, we can just replace this angle NAPB to this one. Okay. So these two are equal, and the same for not this. Well, these two inscribed angles like B1 P and C and B1 C and C. Now we catch the angle NAP and C as a sum of these two angles, like at vertex A and at vertex C. If we repeat everything for point Q instead of point P, and we obtain that this angle NA, Q, and C is also equal to this sum. And now replace, say, NA by NB. We obtained that this circle also passes through NB. This is NB. Sorry. So, and we move in a bit either order. We proved first that there is this circle like NA, P, and B, Q, and C, and then it's easier for us to prove the concurrency of three lines like A and A, B and B, and C and C. Because if we intersect two of these lines, let us intersect NA and C. Calculating the angles again, we see that the point of the intersection lies on this circle. Again, I skipped the details, but inscribed angles plus angle chasing. And since this point, this is, in fact, this is our point N. Okay, it is defined, it could be defined like intersection of A and A with the red circle. And we know that C and C also passes through this point, and similarly, B and B also passes through this point. So first we proved this, the existence of this red circle, and further it's easier for us to obtain that three lines are concurrent. Of course, it could be proved in a bit different way, with different order using Seva sign laws and so on. By the way, this red circle, at least in Russian, it is called the circle of similarity of three figures. And the reason for it, these points like NA, NB, and NC are not only Miquel point for the corresponding quadruples of line, but as usual, Miquel point is the center of spiral similarity. So in fact, NA, the center of spiral similarity of taking vector b1, b2 to the vector c1, c2, and so on. And there are many known results on this circle. Some of them are presented in our problem 13. Yes, and it seems we need one more statement here, that the lines like P B1, this line, and similarly Q B2, such lines also intersect on the red circle. But this is again easily follows from inscribed angles, so you just need to catch the angle between lines PB1 and QB2. Okay. Next, I will move to the problem I think 26, and possibly connect the plot of this problem with some other problems of the project. Okay. Just a moment. I will open. Yes. So we can try to reformulate again this problem. Initially taking a triangle ABC and a pair of isogonally conjugate points like P and P prime. So by definition, we take them as isogonally conjugates. And finally, we, by uniqueness of our construction, we will get that this P prime coincides to Q given in the condition of the problem. So we can start with drawing projections of P and P prime onto the sidelines. And as we know, it's well known, these 6 points lie on the circle, the pedal, common pedal circle of these 2 isogonally conjugate points. And after that, we can let's go back, and after that we can start the following procedure. We can draw these lines. Initially, these red lines, initially they are perpendicular to the sidelines of triangle and pass through P. And now rotate these lines, rotate with equal angle, speed, and as points of intersection with sidelines, we obtain these 3 points like A1, B1, and C1. And in fact, looking at similar right angled triangles PB, B1, and 3 analogous. I'm trying to mark these 3 triangles. They're similar. We realize that this family of triangles like A1, B1, C1 all these triangles are similar to each other, and they could be obtained by a spiral similarity with center P, starting from initial position from the pedal triangle. So the process looks like start from the pedal and rotate and obtain this family of similar triangles. So what about the circumcircle of this triangle and about the circumcenter? Since all the corresponding points move along the lines, yes, it's easy to construct the center of the circle A1, B1, C1. So this center, let's start from again from initial position and check in this initial position, the center is located at point R0. That is the midpoint of the segment PP prime. And then it moves in the following way. Yes, let us construct it. Yes, we call it R. And you see, as expected, this R, this center of green circle, is moving along the line that is perpendicular bisector of PP prime. So, and the reason for it that this triangle like T R0 R is similar to all others brown right angle triangles, like triangle PC C1 is similar to P R0 R, because R0 and R are corresponding points, circumcenters of similar triangles, or triangles that could be mapped one to another by a spiral similarity with the center P. And next, we see the symmetry of this construction with respect to P and P prime. So we can consider the following the similar construction. We can perform the following the similar steps for point P prime instead of P, and consider the lines through P prime are rotated by the same angle, but in the other direction. If we rotate the triple of lines through P clockwise, the lines through P prime will be rotated counterclockwise like that. And we obtain now 3 more points like A2, B2, and C2. And in other words, we need two triangles A prime B, A1 B1 C1 and A2 B2 C2 inscribed in the same circle. And we could call these two triangles so generalized pedal circle of 2 points P and P prime. And we can call this green circle the family of green circles, like generalized pedal circles generated by the pair of isogonally conjugate points P and P prime. Now, this is construction. This construction is nice by itself, in my opinion. But what is more nice thing that it is connected with conics inscribed into a triangle. We can construct the conic with foci P and P prime inscribed to our triangle. I'm trying to do that. And constructing the point of tangency. And we see, let's again move this green circle. And we can see that in most, okay, let's say in most positions, this green circle touches our blue ellipse. And in fact, all this family of generalized pedal circles touch this in some sense, possibly in complex, not real points on complex projective plane. They touch this blue ellipse, twice tangent to this ellipse. What is the reason for it? There are many explanations, and one of the explanations returns us to the problem 19. So looking at this construction, what do we see? We see similar brown triangles, which means that the angles are like these angles between the lines, between the side line of triangle and the segment PC1 is the same angle like at vertex B1 and the same for A1. These angles are equal. And it's not surprisingly that all these lines are tangent to a conic that is twice tangent to our circle. It's a construction of, say, so-called generalized Brocard ellipse. So we have this fixed angle, and we rotate the line PC1, where C1, say, an arbitrary point on green circle, rotate it at fixed angle and obtain a line that touches the ellipse. So it's completely in accordance with problem 19. I just want to mention that this generalized Brocard ellipse appears not only in this project, yes, as this is a page of a summer conference in 2013, and mostly all the project was devoted to Brocard points, and some generalization like Brocard ellipse inscribed in the circle, tangents twice to a circle. And one more thing, some further properties of this conic was presented in our article. Again, it started from definition and many nice geometry properties. If you wish, you could check it. Yes, and we move to problem 31. That is closely connected with this problem, in particular, just in some sense a particular case when P and P prime, this pair of isogonal conjugate points, are Brocard points of the triangle. So we can consider this configuration. Okay. Let us consider Brocard points of triangle. The first Brocard points is here with equal angles, like Brocard 1A B, Brocard 1B C, and Brocard 1C A. And the second is isogonally conjugate to it. And how to connect this famous result on the Brocard circle with diameter OL, where L is the circumcenter and L is the Lemoine point of our triangle. I will try to explain how to connect this, how to put it in the previous general construction. So we consider for this pair of Brocard points, we can consider generalized pedal triangles and generalized pedal circle. It is drawn here. So these 6 points on the sidelines of triangles is our A1, B1, C1, A2, B2, C2. In fact, again, they are constructed in such a way that angles like Brocard 1, this C1, C2, okay, sorry. These angles are equal. And they all 6 are equal. And what do we see? If we consider this family of generalized pedal circles, one of these circles should be just circle ABC. And it's more or less obvious using the definition of Brocard points. One of this circle is ABC, and immediately we obtain from the previous general facts that the point O is one of the centers of generalized pedal circles, and it lies on the perpendicular bisector of the segment between Brocard 1 and Brocard 2. This green line is perpendicular bisector. And one more interesting circles of this family is a circle with center L. So if we move our points so that the center R of this circle coincides with L, then we obtain another interesting circle. In this position, it could be proved that these lines are joining points of intersection are diameters. These lines are diameters of the and all these three segments are anti-parallel to the corresponding sides of triangles. This circle is called the Taylor circle, and it's amazing that this known circle is again just one in our family of generalized pedal circles generated by Brocard points. Moreover, if we consider again all this family of circles and all these positions, we can notice that in fact we consider a hexagon self-intersected in our construction. Hexagon inscribed in this red circle. This hexagon consists of 3 segments parallel to the sides and 3 segments anti-parallel to the sides. This family is known as a family of Tucker circles, and again it's amazing that we have now another description of this family as generalized pedal circles. So maybe I will finish shortly if colleagues have an idea to add something, to comment more. Okay, then formally we close our discussion, and of course you find the more or less complete version of written solutions. So thank you.
Yeah, thank you, Pavel. If no one has any questions, then the next discussion is at 3 p.m. Moscow time. Distance graphs and Turan's theorem. And for now, thank you very much.
Спасибо. До свидания.